All right, so this is the screencast that's going to cover LeChatelier's principle. So what is the purpose of LeChatelier's principle? Really, we've talked about equilibrium, and when a reaction gets in equilibrium, there's going to be that forward reaction, reverse reaction are in balance, so they're going at the same rate. Well, now we're going to tweak with that and see what happens. Because sometimes we need to make more product than what the equilibrium allows us to. So LeChatelier's principle basically says if a stress is placed on a system that's at equilibrium, the system will respond by altering the equilibrium in such a way as to minimize the stress. It's kind of like a positive or a negative feedback system in the body. If you do something to it, then it tries to reverse it. So if I add more reactant, it's going to try to get rid of that reactant. If I add more product, it's going to try to get rid of that product. Basically, it tries to fix whatever I did, whatever I stressed it. So we're going to use this example, the making of ammonia. So if reactants and products are present in a fixed volume, and if I add more ammonia, the system's going to be stressed. So if I add more product, it's then going to push it to get rid of that product, so it's going to make more reactant. If I were to add more reactants, it's going to push it to make more products to get rid of that reactant. So the stress is whatever I do to disturb the equilibrium. So in this case, if I add more product to the system to relieve that stress, it's going to try to remove that. So it's going to convert it back to reactants to get rid of that extra. So if I introduce a product, you can see down at the bottom, the equilibrium shifts back to the reactants. If I add a reactant to the system, if I add nitrogen or I add hydrogen to relieve that stress, it's going to try to remove that added material by converting it to product. So if I add more reactant, then I'm going to make more product. So really, you just have to think about what's going to be the opposite. If I do something, how is it going to fix it? How is it going to correct it? So effective concentration. By adding or removing either reactants or products at a fixed volume is saying that the concentration is changed. So if I'm adding more, then I'm increasing the concentration. If I remove some, then I'm decreasing the concentration. So the system will react to the stress to return the concentrations to their appropriate ratio, not what they were before. You're now going to establish a new equilibrium concentration, but it'll be in the same ratio that it was before. Of products to reactants. So here's an example. If I have iron thiocyanate is a reddish color, and then the product of the forward reaction is yellow because the iron is yellow in the solution. So the first one is showing you the reaction at equilibrium. So it's clearly, because it's yellow, the equilibrium favors the products. B is showing you a shift to reactant. So if I add more products, then I'm going to shift it back to this color, and that's why it turns red. And then C, I can even shift it more to products by adding more of the reactant. It's going to try to get rid of that reactant and turn it more into products, and that's why you see it more yellow. This is the type of stuff that we're going to do in the lab, but you can make predictions by just looking at the color changes or just kind of thinking about if I add more product, it's going to go back to reactant. Well, that's going to make it red. If I add more reactant, that's going to push it to product. That's going to make it turn yellow. Exothermic reactions, we're going to treat heat as a product because remember, heat is given off, so you will sometimes see heat energy listed as a product. So if I add more heat, that's essentially like me increasing a product. So if I add heat, I'm going to push it back to the reactant side. So heat favors, in this case, the blue species. Heat favors the blue species while cold favors the pink. So if I add heat to it, then I favor the reactants, which are blue. And if I take heat away, if I make it cold, then it favors the products. So more product shifts equilibrium to the left. Increase amount of reactants, decrease the amount of products. You basically just have to think about, for an exothermic reaction, doing the opposite. So if heat's a product, then I have to push it back towards reactants. In an endothermic reaction, you're going to treat heat as a reactant. This reactant is going to shift to the right if heat is added by increasing the temperature. So we're going to try to get rid of it. Pressure is the same way, except you don't look at which way it's necessarily going to shift it in terms of reactants and products. You have to determine the number of moles when you look at pressure. So pressure affects the equilibrium only if one or more of the substances is a gas. If they're solids or liquids, pressure really has no effect. So you have to look at the states of matter for some of those to be able to tell if pressure is going to affect it or not. And you have to count the number of moles. If I have like 3 moles on one side and 2 moles on the other side, then pressure is going to affect it. If the moles are the same, if I have 2 moles and 2 moles, then if the coefficients are 2 and 2, then pressure is not going to have any effect on it because they're the same. So if there is a difference in the moles between reactants and products, and there are gases, then if pressure goes up, I'm going to shift to the side with less moles, with fewer moles, so fewer coefficients. And then if pressure goes down, I'm going to shift to the side with more moles. So I'm just going to do the opposite. So in this case right here, we have 4 moles of gas on the reactant side, and we have 2 moles of gas on the product side. So if I increase the pressure, which way will the equilibrium shift? Well, increasing the pressure favors a decrease in volume with more of the product being formed. So if I put more pressure on it, it's going to shift to the side with fewer moles. So it's going to shift to this side, to the products that has fewer moles. If I increase the pressure, that is now going to favor the side that has more moles, so it would favor the reactants. In this reaction right here, they both have 2 moles and 2 moles, 1 mole of hydrogen, 1 mole of iodine, so changing the pressure isn't going to affect this equilibrium at all because they're the same on both sides. A catalyst also has no effect on the equilibrium composition because remember, it just increases the rate of both the forward and the reverse reaction to the same extent. So it's not like it's increasing one and decreasing the other. The catalyst is making the overall reaction occur faster. So a catalyst does not affect equilibrium. It's not going to change the composition or the concentrations of anything. So what we're going to do in the lab is you guys are going to mess with a system. You're going to let a system get to equilibrium, and then you are going to try to figure out what the reaction does. Does it shift to reactants? Does it shift to products to try to undo whatever you did?